So today we're going to talk about addition reactions that result in organic halide products. So you've learned about naming organic halides, and now we're going to get into how we actually make them. So this is another addition reaction. You learned about addition that was hydrogenation, so just adding H2 to unsaturated hydrocarbons in order to make other hydrocarbons. So now we're dealing with making derivatives, hydrocarbon derivatives. And what I'm doing is I'm making organic halides. Now, addition is always reacting with an unsaturated hydrocarbon. So no matter what, I'm going to be reacting something with a hydrocarbon that has double or triple bonds. But here what I'm doing addition resulting in organic halides is I'm reacting some kind of unsaturated hydrocarbon with either a halogen molecule, right? So like Cl2, for example, or a hydrogen halide, so HCl, where I have one hydrogen and then one halogen connected together in a small molecule. So an addition reaction in which fluorine, chlorine, bromine, iodine, hydrogen, or any combination is added to an unsaturated hydrocarbon to reduce the number of multiple bonds. That's generally addition, but we're going to be adding halide or halogens or hydrogen halides to alkenes or alkynes. So for example, if I took ethionine and I reacted it with chlorine, well, just like in hydrogenation, where an H added to one carbon and H to the other carbon, then the double bond got broken. Here, instead of an H, it's a chlorine. So one chlorine adds to here, another chlorine adds to here, and this double bond goes away, and I end up with 1,2-dichloroethane. Where students often get confused is they want to add both chlorines to one carbon, but we have to remember that this double bond is breaking, which now allows each one of these carbons to form a new bond, and each one takes one atom out of this two-atom molecule. All right, here's another one. Ethionine and bromine, but now it's an excess. So because I have a triple bond here, this can essentially react twice in order to give us an excess 1,1,2,2-tetrabromoethane. So reacts once, bromine goes here, bromine goes there, right? I end up with 1,2,2-dibromoethionine, and then it reacts a second time because it was an excess to get 1,1,2,2-tetrabromoethane. If this was given to you as an example or as a question, you wouldn't have to do this junk. You would just go straight from here to here because it is an excess. So I add two bromines, right, to each carbon because I broke two bonds in order to add this to the compound. In each reaction, the halogen adds to the multiple bond, distributing an atom onto each side of the bond as it is breaking. This causes triple bonds to become double bonds and double bonds to become single bonds. But again, because it was an excess, it happened twice. Now, here's where this gets interesting. When I add hydrogen halides, so I have one halogen atom and then hydrogen, and when I add that to my unsaturated hydrocarbon, what's interesting is I can make isomers. So because one of the carbons will take the hydrogen and the other will take the halogen, as a result, that can actually make two different compounds because it could flip, right? So for example, if I'm reacting HCl with propanine, the H could add to the first carbon and the Cl to the second carbon, and that would end up with 2-chloropropane, this product here, right? H, let's look at it from this side. H added here and then Cl added. So this was HCl. H added to this carbon, Cl added to this carbon. Or it could go the other way around. So the Cl could add to the first carbon and the H to the second carbon, which would end up with 1-chloropropane. So that was this product. Both of these products would actually get made in this reaction, and it's important when you're doing the work that you show both products because both products do get made. If I did this reaction in real life, I would get some of this and some of this. I would actually get a mixture of both products actually being formed. And the interesting thing about organic chemistry is we can make the conditions so that one product forms more than the other product, but it's interesting that we do get both isomers. So pay close attention to the different isomers that would occur, although figuring out what percentage of each product would occur is far too advanced. That's the wrong two. For this course, we must be aware that a certain amount of each would be produced, and therefore all isomers should be included. So we have to draw them all. Now that was really quick. We need to go through some more examples that we actually actively do. So why don't we go ahead and create a new page here. Oh, what am I doing? Yeah, redo, undo. Let's get out of that. Come on. Yeah, new page. And let's go ahead and try something interesting. Like, let's react with a cyclo. That could be fun. So let's go ahead with a cyclohexane. This is not benzene, by the way. And we're going to do this with a line diagram just for kicks. And let's react to this with hydrogen iodide. So my question for you is, what products would I get from this? I really should draw this out as a condensed, because I think that will help you make a little bit more sense of this. CH2, 2C, this has a CH3, and I have a double bond to a CH here, and a single bond. Okay, so this is what I have, and I'm reacting it with HI. So right now what I have as a structure is 1-methyl cyclo hexoneine. And I'm adding to this hydrogen iodide. Okay, so when I add this, one hydrogen could add to this carbon and the other I could add to this carbon because I'm breaking this double bond, right? Or the I could add to this carbon and the H could add to this carbon. And in fact, I get both products. Both end up getting made. So I end up with CH2. Let's do the C here. Let's do the first one where I add the H, and I'm going to draw it separately just to kind of really show what's happening there. And then on this carbon, I have the bond to the CH3, but I also have a bond to my I, right? Because it added to that one. Then I have CH2, CH2, CH2. Sorry, this was a CH2. My bad. Like this. So I broke my double bond to add the hydrogen and the iodine, so I end up with that product, but I also end up with the product where the I adds to this carbon and the H to this carbon. So how that would look is I would have CH going to an I, then I would have this carbon, which now has the CH3, and I'll draw the H separate as well. Not necessary. You could draw this as just CH here, but I want to show that that added. Then I have CH2, 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 and then my bond right there. So this is another way for hydrogen iodide to add. So I made two different products. Now let's name both of them. I comes before M in the alphabet. So I have, for this particular structure, I'm going to draw a line over here to not be smushed. 1-methyl, 1-iodo. No, I is before M. Oh, yuck. I is before M. My bad. Alphabet. Yeah, that's the hardest part of this, is remembering your alphabet. 1-iodo, 1-methyl cyclohexane. Notice that it's now ane because I have all single bonds here. And this would be the first carbon, right? Because it's the only thing I have anything on. So this has to be carbon number 1. Now for the next one, I need carbon 1 and carbon 2. So because iodo, I is before M, this is going to be carbon number 1. This will be carbon number 2. So here I have 1 iodo, 2 methyl cyclohexane. Cyclohexane is the name. All right, so that's another example where you can kind of see how it can add in two different ways. Now, if this were just, let's say, I2, I and I would only have one product because I'm adding the same thing to both carbons. So in that case, it would just be 1,2-diodo, 1-methyl cyclohexane, right? Something like that. So just interesting, when I have hydrogen halides that I'm adding, it ends up with different products than I would get if I wasn't adding a hydrogen halide, but just a halogen. Okay, hopefully that makes sense. Have a good rest of your day.